Hi class. In this video, I'm going to go over one of the examples in section 5.5 about the SIR epidemic model, because it seemed like if you are going to see any one real-life example of differential equations in 2021, you probably want it to be the one about epidemics. So the Seer model you've probably kind of heard of if you've read anything about the pandemic. And what it stands for is it's a model for sort of counting up the relative numbers of the population of people who are susceptible to a disease. So this is S stands for however it's spelled, susceptible. I is infected, and R is recovered. There are some similar models that have slightly different acronyms because they include other sort of types of populations, but this is the simplest one. So we have a quantity S of t, which is the number of susceptible individuals. And we also, a sort of more useful quantity is going to be, we're going to call little s, so that's a little s, which is equal to big S divided by n, where n is the population size. All right, so big I of t is equal to the number of individuals who are currently infected. And so similarly, we're going to take little I to be equal to big I divided by n. And our last quantity, big R, is the number of individuals who have recovered. And same thing, we get little r is equal to big R divided by n. So how do we actually write differential equations for these quantities? So let's think about this. So in a unit of time, say like a week, someone who's infected will encounter, let's say, A people and expose them to the disease. So that means that A times the number of infected people will be exposed. But the only people that will then become infected, of those exposed people, they'll only become infected if they were susceptible to begin with. Okay, so there's only a fraction of the total population are susceptible. So little s equals big S over n is the fraction of the population which is susceptible. So what that means is that in a unit time, S times AI go from susceptible to infected. Okay, so what that means then is that d big S dt will decrease by that amount. So equals negative SAI. And we can divide this whole quantity by n, and we get d little s dt equals negative as little I, because when you divide this right-hand side by n, you divide the big I by n and you get little I. So you may have heard of this quantity R naught, which is really important for how COVID was spreading. And in some situations, we had like an R naught that was bigger than 1, and that means that that any infected person is like infecting that many people, like more than one person, and so then you get this exponential growth, and that's equivalent to the parameter A in this example. Whereas if you like quarantine people that are infected, then the A is going to be smaller because they only get a chance to, maybe they only get a chance to infect the people that they live with, or the people that they're exposed to, which is fewer people since they're quarantined. Okay, so that's our differential equation for S. Now, what about I? di dt, how is the infected population changing in a unit of time? Well, it's growing by the same discussion that we just had before. It's growing by SAI, the number of people that out of the susceptible population that we got. But it's also dropping by a rate of K times the size of the population, where K is the recovery rate. Say you recover, it depends on how long it takes you to recover. And so we can rewrite this one like A times S minus K over A I, and that's going to be useful for us later. And then we divide, we're really interested in the rates here, or the proportional quantities. So we're going to divide everything by n again, and we get d little I dt equals A S minus K over A times little I. And then the last quantity, the last equation that we need is d big R dt. So that's the recovered population, and that's going to recover by the same amount that the infected population, or that's going to grow by the same amount that the infected population fell. So dr dt equals Ki, and so we could divide by n, and we get d little r dt equals K times little I. And it's important to note that the population of everything, S plus I plus R dt, equals, if you add everything together, you get negative SAI plus SAI minus KI plus KI, big I, and that is all equal to 0. Because the population size, so the total population size, doesn't change. And the way that this kind of can make sense in reality is that if anyone dies, you sort of include them in that recovered population, which is a little grim to think about, but it helps with the simplification of this model. Okay, so I'm going to write everything out again, just because I can. ds dt is negative as I, di dt equals a s minus k over a I, and dr dt equals ki. So this is our system of equations. Now, why do we model things? It's to know what's going to happen as time goes on. Okay, so if we know, let's say we know how many susceptible people we have right now, we know how many are infected and everything like that, and we want to know what's the path that this epidemic is going to take as we go on into the future. And that's where understanding these rates, these differential equations, and being able to understand the behavior of the system is going to be helpful to us in the real world. So we have seen this is a system of 3 equations, and most of the stuff that we've done so far has been a system of 2 equations because it's a little bit more tractable for us. So we'll note that S and I, our equations for that, don't involve R. So those 2 don't include R. And they also don't have a T in them. So they're like autonomous systems like we saw in the phase plane discussion. So we can do phase plane analysis on just these 2 equations. Okay, let's think about our equations a little bit more. That's what we wanted to do. Okay, so let's start with ds dt equals negative ASI. Let's think about the behavior of that a little bit before we get on to the phase equation. So we can kind of separate out the variables, and we get 1 over s ds dt equals, we can write this as d dt of ln of s, right? That's kind of chain rule, and that equals negative ai. So if we integrate from 0 to t, we get that the ln of s equals the integral from 0 to t negative ai plus a constant dt. And if we solve that, we get s of t equals the initial value times e to the 0 integral blah, 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 all this stuff, ai dt. And that's like kind of like solving a linear equation or solving a separable equation. And so the thing is here is that this is positive if we start off positive. Okay, so similarly for I of t. So what we have found is that s and I never change sign. If they start off positive, which of course they are, because the number of infected people or the number of susceptible people is never going to be negative. So if they start off positive, they stay positive. All right, so that observation we're going to need in a little bit. So let's go back to our system of just s and I. So we have ds dt equals negative asi, and di dt equals a s minus k over a I. So what are our critical points? So that's what we get when we set both ds dt and di dt equal to 0. So if we have negative asi equal to 0, and I'm going to expand out di dt to write asi minus ki equals 0. So if negative asi equals 0, then we get, that sort of cancels that one out. So both of these together imply that negative ki equals 0. But k can't be 0 because it's our constant. So we get I has to be equal to 0. That's the only critical point. Or the only sort of criteria. There's no restriction on s, and so that kind of makes sense that I of t is the number of infected per the population, and so that's the sort of the stable point where we have no infected people anymore. So if we look at our equation for s, it's decreasing. A, s, and I are all positive numbers, so d s dt is negative. So s of t is monotonically decreasing. And it's bounded by 0 because of what we were talking about before. If you start off positive, then you stay positive. So it's bounded by 0. Therefore, it has a limit. So s, we'll call it s infinity, equals the limit as t goes to infinity of s of t. This exists. And this is interesting to us because by the theorem, which I talked about in section 5.4 about the phase plane, by theorem 1 in section 5.4, if s infinity and sort of the same concept, I infinity, the limit as t goes to infinity of I, both exist, then that point, S infinity, I infinity, is a critical point. So now let's move on and look at the phase plane. We kept talking about the phase plane, but now we're actually going to write it out for this system. So that's going to be di ds. So it's di dt divided by ds dt, which is equal to asi minus ki over negative asi, which equals -1 plus k over as. And so this is actually like pretty easy to solve. It's actually already separated for us, right? We can kind of flip the ds over there and we get di equals -1 plus k over as ds. And we can integrate it because it's all right, separable. And so then we get I equals -s plus k over a, that's just a constant, ln of s plus another constant. So now let's think about our behavior at infinity again. So as t goes to infinity, we know that there's a limit on s, but we can see from this that s of infinity can't be 0. Otherwise, ln of s infinity would be -infinity, right? So this term would go off to -infinity. So that's not good, okay? So then we have that s infinity is some positive number. So if this ln term went off to -infinity, then your I would be negative, which we know we can't have. Okay, so now we can actually plug in. So now we get that the limit as t goes to infinity of I of t would equal the limit as t goes to infinity of, -s plus k over a ln of s plus c, which would equal, -s infinity plus k over a ln of s infinity plus c. So that exists. And so therefore, s infinity and I infinity is a critical point. But we already talked about on critical points that we have to have I equals 0 in order to be a critical point. So therefore, we also get that I infinity equals 0. So as time goes on, you'll get some limit on the number of susceptible people, and the number of infected people will go down to 0 eventually. And so the last thing to note, we'll go back and look at our equation for di dt. So let's just write it again. So if s of 0 starts off at some value bigger than k over a, then di dt is initially positive, right? Because this quantity would be positive. So that means that the number of infected people is going to increase until the number of susceptible people drops down smaller than k over a, and then I starts decreasing again. And that's kind of like that herd immunity concept where you have so many people that are not susceptible anymore, either because they've already got the disease or hopefully in our case now that because they've been vaccinated, that now that I will then start decreasing down to 0. Then eventually I decreases to 0. The idea, the point here is that by building these models, you can start to look at the behavior and see what's going to happen over time and see what variables kind of need to be changed and what kind of behavior you can expect. And you use all these techniques, just like kind of basic solving linear equations or using the phase plane analysis that we saw. And there's some examples. There's an example of the book where they actually plug in the actual numbers from an epidemic, from a flu epidemic, so that you can see where that, you can use these models to see like how many people are going to have to be infected before we start decreasing. What does this K over A mean? What are those constants and what do they mean in our real life? And so that's what epidemiologists do and how they use these types of models.